Good morning everyone. Today we are going to take a look at our MicroDev boards, which is a series of small form factor development boards designed around various popular microcontrollers. Currently we have 4 variants in total, one with an ESP32S3, another one with an RP2040, also known as the Pi Pico, and then we have 2 variants with STM32 processors, a F411 and a L072. All of these dev boards are more or less identical in design, as we will soon see. The only difference is of course in the provisions needed for their respective microcontrollers. So we will start off by having a look at this generalized block diagram that we have in front of us, as it gives us quite a good overview of the features of the MicroDev boards. We will also briefly go through the different variants of the MicroDev boards and see how they differ from each other. After that we will move on over to the schematics for a closer look at how the circuits actually work. Once we plowed through those, we'll finish off with a quick rundown of the layout and the actual PCBs themselves. Now, let's begin with this generalized block diagram. We'll start off in the top left corner, where we can find our power inputs. Weird how we always seem to find the power inputs in the top left corners of schematics and block diagrams, but anyways. Our main power input is this USB-C port. It will of course supply our system with 5 volts, and we also have the 5 volt rail from the USB-C port broken out on a pin called VUSB. This allows the user to access the 5 volt supply from the USB on the breadboard, which the MicroDev board then plugs into. Furthermore, we have a V-in pin. This pin accepts inputs ranging from 3.5 to 6.5 volts. These 2 power inputs are then fed into something I've chosen to call an automatic power switch, which is just a fancy way of saying a MOSFET and a diode that makes sure that the USB power is always prioritized as the power. Moving on to our right, we find the MicroDev's linear regulators, and it appears to be 2 of them. Well, why might that be? As we can see, one of them is labeled as System 3.3 volt regulator, and that is quite self-explanatory. It's the internal 3.3 volt regulator for the microcontroller and its supporting circuitry. The output from this regulator is also broken out to a pin that's called 3V3, making it accessible on the breadboard as well. Now, what about the other regulator labeled auxiliary? Well, this is also a 3.3 volt regulator, and its output is also available on the breadboard through the out pin. But there's also an enable signal. Now this enable signal is quite nifty, as it can be controlled by the microcontroller on the MicroDev board through the pin X, or via an external signal on the out EN pin. This means that we can turn on or off the output of this regulator as we see fit, and more specifically power down any external circuitry that is supplied by this auxiliary power regulator. Moving further down, we see an onboard LED that can be quite handy for debugging or perhaps even just as a power indicator. This LED can, just like the auxiliary regulator, be controlled by either the microcontroller on the MicroDev board itself through pin Y, or by an external signal on the LED pin. And just to clarify, all the orange pins shown in the block diagram will of course have labels corresponding to the specific microcontroller on the MicroDev boards. This also goes for pin X and Y. For example, on the MicroDev ESP32-S3, pin X is labeled and connected to GPIO21 of the ESP32-S3. And finally, the microcontroller itself. Well, as this is a generic diagram, there's not much to say here, except for mentioning the exposed programming ports. Either one can program the board through the USB-C port and the Arduino IDE, which makes the process very simple and very beginner-friendly. Also that means one can take advantage of the whole Arduino ecosystems with libraries and so on. However, if one is feeling the urge to dive into the rabbit hole that is embedded programming, each MicroDev board also has an exposed programming port that allows you to program it through any IDE of your choice. For instance, the MicroDev STM32F411 could be programmed through STM's own IDE called CubeIDE. This additional exposed programming port is an SVD port, serial wire debug, except for on the MicroDev ESP32S3 where it's an UART port. Now that's it for the generalized block diagram. Let's continue on with each individual MicroDev board. Okay, so now we're in the MicroDev ESP32S3's datasheet. And I guess the ESP doesn't really need too much of an introduction, right? I think most people are kind of familiar with these types of processors since they're very popular in the maker community and for hobbyists and so on. But anyway, we'll run through this pretty quickly. The core is a Xtensa 32-bit dual core. It can run up to 240 MHz. The particular S3 that we're using has 8 MB of built-in flash. There's also some SRAM if you want to play around with that. And then of course we have the Wi-Fi and Bluetooth capability of the ESP32, which makes it so popular. Other than that, we do have a few digital interfaces we can play around with. SPI, I2C, even I2S if you want to do some sound stuff. We have CAN. And of course, as you've come to expect by now, microcontrollers these days always come with a bunch of ADC channels. On the ESP, these are also touch sensing capable. We have a few timers and also a bunch of PWM channels, also these motor controlled PWM channels that we could play around with. Now, if we scroll down a bit, we'll find a nice little view here, a simplified view of all the features that's available on the MicroDev ESP32 board. And we could quickly just have a look and see what we can find here. We'll zoom in a little bit. And here we can see we have the USB port that we talked about from the generalized block diagram. We also recognize a lot of these pins here that we talked about, the 3v3 pin, the out pin, VUSB pin and so on. And we can also see here that, for instance, the LED pin is connected to GPIO 41. We also have a reset button and a boot button. These buttons are then used when we want to program the board or even just reset it. And up here we can find the UART that allows us to program this board through any IDE of our choice. Next up is the RP2040. This one is also a dual core. However, this time the architecture is ARM and it's the M0 Plus core. It can run up to 125 MHz. We have 16 megabytes of flash on the board, and also there's 264 kilobytes of SRAM built in. Other than that, we do have two of these PIO blocks, which are very popular in the Raspberry Pi community. You can do pretty cool stuff with those. We also have the ability to use DMA. Other than that, of course, a few digital interfaces. And also, in this case, actually just a few ADC channels, which is quite uncommon, I would say, nowadays. However, PWM channels, there's a bunch of them, and we do have a system and a watchdog timer as well. Now we can scroll down again and just have a quick look at this simplified functional description here, just to familiarize ourselves a little bit with the board and see that it does look physically different from the ESP board. However, the power input is basically more or less the same. We have our 16 megabytes of flash here, and also we have our boot button and our reset button. However, it's called run here on the RP2040 and USB boot. Now for the RP2040, if you want to program this through something else than the Arduino IDE, we will use our serial wire debug port, which we have up here in the left corner. And that's about it. We've also marked out the ADC channels here just because there's a few of them to make it easy to find. Okay, Now let's move into the territory of STM32 and also perhaps into a more professional territory, if I dare say so. I know from my own experience at my regular workplace we do use these types of processors in most of our products, and it kind of shows a little bit when we take a look at the flash, for instance, and the SRAM. All of a sudden we do not have as much memory to utilize on these guys. But anyway, this is the F411. It is a Cortex M4 ARM core. It runs at 100 megahertz. It comes with 512 kilobytes of flash, which might not seem to be that much compared to the ESP, but if you program these through the STM Cube IDE, you're gonna be fine most of the time. We also have 128 kilobytes of SRAM to play around with if we would like to. Then again, a bunch of digital interfaces, SPI, I2S for sound, I2C of course, a bunch of UART. Now we're gonna take a look at this in a little bit, since it's a bit more tricky to use these than what it is on the ESP32, but we'll come to that later on. Of course, we have our ADC as well. We've got 9 channels on this one. We've got a few timers here as well, also a bunch of watchdog timer and system timers and so on. And we have our 2 DMAs with 8 channels, which allows us to do quite cool stuff if we want to. Now we'll scroll down a little bit and we'll get to this simplified functional description again. Now we've looked at these a few times, so I'm not gonna spend too much time here. We sort of know the gist of this right now. But as we can see, we have our reset button and our boot button again, and also we have this zero wire debug port where we can program the microcontroller from the Cube ID if you don't want to use the Arduino ID. Now for the pins, we have this long list here which helps you figure out which peripheral you can connect to which pin. On the ESP you can more or less connect any peripheral to whatever pin you want with some restrictions, but for these STM processors you are way more restricted. So as you can see here, we have labeled all of the peripherals here that you could connect to pin A0. So for instance, you could use timer 2 channel 1, or you could use UART2 for instance, the CTS pin, and you also have ADC 1 channel 0 here. But as you can see, you could for instance not connect ADC 1 channel 2 to this pin, right? Then you need to find ADC 1 channel 2, which is here, and use this pin for that. Now for the last variant of the MicroDev boards. This is again an STM32. However, this time it is the L072. L0 basically stands for STM's low power series, and as we can see down here, it does perform pretty well in its various sleep modes. We can see here, for instance, in deep sleep mode we end up with a current consumption of about 87 microamps, which is kind of nice, making this board extremely good for battery powered applications that you want to keep running for a long time and so on. Now, since it is a low power variant, it does unfortunately, I probably shouldn't say unfortunately, but logically enough, it does come with a weaker core. It's the M0 Plus core, and it only runs at 32 megahertz, and it has even less flash than the previous STM variant that we looked at, 128 kilobytes in this case. We do have a little bit of EEPROM built in, which is kind of nice, and also rhymes well with the whole low power thing. You would perhaps want to save certain data to the EEPROM while you're powering this thing down, and then all the variables are scrubbed away and so on. So that's nice. We also have a little bit of SRAM here, 20 kilobytes. Here we can find our digital interfaces. So we have SPI, I2C, and so on. And we also have one of these low power UARTs, which is very nice for your low powered applications. Going further down, we do also have an ADC with 9 channels, but we do also have a DAC, which is kind of cool, or 2 of them to be exact. Most likely left to right channel if you're doing some sort of audio project. We have touch sensing capability as well, which is also pretty nice. We also have 2 ultra low power comparators, again for your low power projects, some timers, and also real-time clock and system timer, which also of course plays well with the whole low power thing. Now again we can scroll down a little bit and go and take a look at our functional description here. We've seen this probably enough times now to understand how this works, but we have our reset button here, our boot button here, again our 0Y debug port here if you want to program it for something else than the Arduino IDE. And again, since this is an STM processor, we need to be mindful of what peripheral we want to use and which pin it is connected to. Let's continue on with a quick look at the schematics. We've been dragging on for quite some time now, so we're not gonna do a deep dive into the circuitry here. We're just gonna have a quick look, a little overview. And I've chosen to open up the ESP32S3 schematic, since we do have this cool Wi-Fi antenna here going on, which makes this a little bit more interesting than the other schematics. But other than that, they're the same. The power block up here is identical on all the MicroDev boards. And then of course there are some differences here depending on the microcontroller, but all of them have their coupling caps and perhaps strapping pins and so on, whatever might be necessary to make them tick. In any ways, we're gonna start up in the left corner again. Take a look at the power block. And what we can see here is our USB-C port up here. We have 2 5.1K resistors connected to the CC1 and CC2 lines. They're pulled down to ground. This tricks any USB-C PD capable power supply, that is power delivery capable power supply, to give us 3 amps on the USB line, which can be kind of nice. Other than that, we have this simple little IC that contains a bunch of ESD protection diodes here. As you can see, we are ESD protecting the USB line itself and also the data plus and data minus lines. Moving on, we have this automatic power switch, and as we said before, it's just a fancy way of saying a diode and a MOSFET that makes sure that we always prioritize the VUSB line. Basically this is a PMOSFET, so if you have a voltage here that is similar to this one, he won't conduct. But if you remove the voltage here on the VUSB line, he will be pulled down to ground and start to conduct. The diode and the MOSFET together also gives us some reverse polarity protection. And here we have our 2 linear regulators with some decoupling caps. And these guys, we chose these because they are physically very, very small, and they come with an enable signal, allowing us to control the auxiliary regulator in a very neat way. Alright. And now for the actual microcontroller, we'll start off over here with all the boring stuff, the decoupling caps. We do filter these 2 pins, pin 2 and 3, VDD 3P3. This is recommended from the datasheet from the ESP32 itself, not from our datasheet, from the actual manufacturer of the microcontroller, that you should filter these supply power to the Wi-Fi circuitry, and can apparently become a little bit noisy. All right, let's continue on. Up here we have our Wi-Fi antenna, and also we require this impedance matching network. Now there's a whole lot you could say about impedance matching networks, and we're not gonna go through it here, but basically we're trying to make sure that we can transfer all of the power out from the ESP to the antenna. We're trying to get rid of reflections and so on. So we're trying to match the impedance of the circuitry inside here with the impedance of our antenna. We have actually fine-tuned these values based on some empirical tests we did, even though we did calculate them, of course, at first, but we noticed that we did get better results if we trimmed these a little bit. Okay, over here we have our onboard LED, not much to see here. And down here we have our crystals. We have the main crystal, a 40 megahertz, and we have our real-time clock crystal here, 32.768 kilohertz. For the ESP32S3, you need these, sorry, not the boot button, but you need these strapping pins. But we also, of course, then have our boot button and our reset button. And to the right here, we just have our I/O. Not much to see here. All right, we're in KiCad's PCB viewer, and we're going to take a look at the PCB. But let's try to wrap this up now. We've been going on for quite some time. We can see here that we're using a 4-layer stack up. The bottom layer we're using for routing power. The lowest internal layer we're using for signals, and the highest internal layer we're using as a dedicated ground plane. And the top layer we're using for signals, and of course some ground when we're jumping vias up to the top layer. We were forced to go down the route of a 4-layer PCB since the PCBs are so small. You can see here it's about 20 millimeters times 48 millimeters, and it was basically impossible to route out all of the traces on a 2-layer PCB. There are also, of course, a bunch of advantages with a 4-layer PCB for EMC, and also for when we want to impedance match our traces for the USB, and in this case the Wi-Fi antenna, of course, which is quite important. Okay, let's zoom in a little bit. Starting from the bottom, we have our USB port down here, and we have all of our linear regulators and the automatic power switch and so on. And then for the ESP, the 2 buttons are located here. We have our real-time clock crystal, we have our main crystal up here, and then also here we do have our filtering for the power supply to the Wi-Fi circuitry, and up here we have the actual Wi-Fi trace going into the impedance matching network. It moves up along here amongst this sea of vias, ground vias, up to a ceramic chip antenna. And as we said before, we have tried to group our signals on different layers. Let's hide the zones, and then if we jump into the layers here, we can see we're basically just routing power on the bottom layer. All of these are power stuff. And then we have our internal signal layer, the orange layer, and then we have our dedicated ground plane, which we can't see because we have hidden our copper pores. But here it's a dedicated ground layer. And then finally our top layer, which then becomes mixed signal and power. Alright, let's take a look at the actual 3D view of the PCB. Where we can take a look at our beautiful silk screen, which has our logo on it. It also has all of the pins written out here. For the ESP, number 8 here, for instance, represents GPIO number 8 or GPIO 8 to make it easy for connecting wires on the breadboard to this thing, so you don't have to check the datasheet all of the time. We also find, of course, our special pins, if you like to call them that. We have the VUSB here, the V-in. Over here we see the UART, the exposed programming port is also shown here with the exposed UART here. Right, we also have our logo on the bottom, of course, trying to promote this thing as much as possible. And lastly, we do also have these pin numbers are in parentheses, and that's because these are the internal LED and the enable signal to one of the linear regulators. So we put those in parentheses to sort of bring attention to the fact that these are actually connected to something else on the PCB as well. So if you want to use this thing, keep in mind that also enables and disables the auxiliary linear regulator. Same goes for this one then, of course, but for the LED. That's it for the MicroDev introduction video. Thank you so much for watching, and I hope to see you again soon. Bye bye.